All right, now that we have proved the fundamental theorem of calculus part 2, let's use that. We can now use that because we believe it, right, to help us prove part 1. So it's kind of interesting that we still call part 1 because in some ways it's the more fundamental of the fundamental theorem. It's the existence portion, right? But the proof of part 2 is the one that's in some sense the first building block, because we're going to use that to help us prove part 1 now. So just like we did in the proof of the theorem for part 2, let's start by writing down our assumptions. Whoops, I have the wrong thing going here. So let's start by writing down our assumptions. All right, the only assumptions for the fundamental theorem part 1 is that f is a continuous function on this interval from a to b. All right, and then the conclusion of the fundamental theorem is that this function, if we call this g of x, the interval from a to x, f of u du, that this is an antiderivative of little f. Okay, so let's use this to prove. Let's use part 2 to prove part 1. So the idea here is that we are going to say, let's suppose that capital F is an antiderivative of little f. All right, capital F is an antiderivative of little f on this interval from a to b. Then, really all we have to do to prove this one is to compute. So remember, first of all, I'll just write down what it means, but this means that f prime of x, big F prime, is equal to little f of x for every x in this interval from a to b. All right? So let's, I'm going to go to a new page, but what we need to show, so TBS here, this means to be shown, or to be proved, TBP you could use. What we need to show is that g prime of x is also equal to little f of x. All right, so this doesn't mean that capital F and little g are the same function, but it does mean that they have the same derivative. So that's what we're going to try to show here. And if we can show this, then we've proved the theorem. All right, so let's write this down. So let's take our function g of x and let's actually compute it. All right, so if we believe that we have a function capital F of x that's the antiderivative of little f, then this integral can be written as the integral from a to x of big F prime of u du. And then the fundamental theorem of calculus, so FTC part 2, tells us that this integral is just the difference of capital F of x minus capital F of a. Okay, so this right here, this is all the work being done by the fundamental theorem part 2, which we painstakingly proved using a Riemann sum argument. Now we don't have to use the Riemann sum. We've already got that result, right? So we can use this. And so this means that little g of x is equal to big F of x minus big F of a. Here, x is a variable, a is a constant. So big F of a is also a constant. And all that we have left to do is take the derivative then, right? So g prime of x is equal to the derivative of this difference, f of x minus f of a. The derivative is linear, so it can distribute to each part, and so we end up with f prime, big F prime of x, minus the derivative of f of a, which is, and this is not the derivative of f applied to a, this is the derivative of the number f of a, and as we know, derivative of a constant is just 0, right? So that part's 0, and by our assumption, big F is an antiderivative of little f, so this is just little f. All right, and so then, just like that, we've got g prime of x equals little f of x. And our conclusion then is that, yes, indeed, this function right here, g of x, this is an antiderivative of little f.